Today we're going to discuss with you about numerical index. Sometimes we find out the numerical index by adding the digits of our birthday together and considering it our own lucky number. We use it for the valuable numbers we possess, which can be chosen as we want. But today, we're gonna teach you some kind of mathematical executions we can do with the numerical index, which are more complex than finding out the lucky number. Come and enjoy art science, which touches the artistic places of science, and makes people informed. We can use numerical index to check whether any number is exactly divisible by 3 or 9, to find what the remainder is when any number is divided by 3 or 9, and to check whether the results of mathematical executions, such as addition and multiplication, are correct to some extent. And also we can use another process just like the numerical index related to 11, in order to carry out the above execution done with 3 and 9. If you watch this video till the end, you may certainly gain a complete knowledge and understanding about the above facts. First, I will introduce you the executions done with 9, which are quite easy to understand. If we want to check whether any integral number is divisible by 9, we have to add its digits all together. If the total is a multi-digit number, add its digits too until you would find a single-digit number, which is called the numerical index of the particular number we have had. If the numerical index is 9, the number is exactly divisible by 9. Or unless it's not. If the numerical index is 3, 6 or 9, the number is exactly divisible by 3. Or unless it's not 2. Since this numerical index is 8, this number is exactly divisible by neither 9 nor 3. Then let's inquire what mechanism takes place in this process. Let me choose the number 1548 as an instance. The number is up to thousands place. It contains a single thousand, 500s, 4 tens, and 8 units. 1000 equals 999 plus 1, 100 equals 99 plus 1, and 10 equals 9 plus 1. So we can replace those as this. 999, 99, and 9 are multiples of 9. So we can take them to the front. Lastly, the number consists of a multiple of 9 and the sum of its digits. 1, 5, 4, and 8. This part is divisible by 9, as it is a multiple of 9. For our number to be divisible by 9, this part also must be either 9 or a multiple of 9. Hence, if the numerical index is 9, the number should certainly be divisible by 9. Then how about the sum of the digits of a particular number being possessed more than one digit? It must be a multiple of 9. And what is the way of finding if it is so? Carry on the same method. Add again the digits of that sum together, and check whether it is 9. The sole mechanism continues. Cause it is another real number, according to the above way, the sum of its digits also should be 9, in order to be divisible by 9. That's why I told that you have to add the digits together again and again, until you can have a single-digit number. If it is 9, the number is divisible by 9. Or unless it's not so. Okay, then let's inquire what the mechanism is inside the rule related to 3. We brought our number 1548 up to this level. Since this part is a multiple of 9, it is also a multiple of 3. Cause 9 is divisible exactly by 3. Then if this sum of digits is a multiple of 3, the number is divisible by 3. If this sum is a multi-digit number, we can add its digits, until we can find a single-digit number, utilizing the same process and mechanism. So we have to add the digits of the number together until we can reach to a single-digit number, and check whether it is 3, 6 or 9. If so, the number is divisible by 3, without any remainder. As well, we can do some more advanced tasks correlating with these. Let's see what they are. As we previously mentioned, any number consists of a multiple of 9, which can be either 0 or non-zero, and the sum of its digits. Since the very sum of those digits is another number, it can also be written as a combination of a multiple of 9 and the sum of its digits. This can be continued until a single-digit number is left which doesn't consist of a non-zero multiple of 9. For that, What is required? That digit should be less than 9. Then that single-digit number will be the remainder when the particular number is divided by 9. Why? 'Cause we've already cast out all the 9s of the number. Also, we can use this for the division by 3. Then what about the final result being greater than 3? Could we admit it as the remainder? No. How could we do so? How could it remain a number which is greater than 3, after any number is divided by 3? Here we have to subtract the closest multiple of 3 which is less than it, from the finally left single-digit number. Then it comes the remainder when the particular number is divided by 3. 'Cause all the 3's have already been extracted as 9's. Then I'm gonna introduce you an important usage of the above invention. Often when we do mathematical calculations, a doubt is left with us whether it is correct. If we can check them to some extent even, it'll bring us some solace. We can prove the additions and multiplications we do, by using the numerical index, to some extent. In the addition process, you have to find out the numerical indices of the two numbers to be added, by adding their own digits each number again and again, until we can reach to a single-digit number. They are the remainders after those numbers being divided by 9. Then add these remainders together. If the final answer we get is more than one digit, take its numerical index. If you've done the addition correctly, this answer and the numerical index of the result of addition must be similar. Otherwise it tells that you haven't done the math successfully. In this example, both of them are the same. So we can have some idea that we have done the aforementioned math accurately. What do you think about multiplication? In the multiplication process, when you multiplied the numerical indices of multiplicand and multiplier, it must be the same with the numerical index of the product. Again, I say that we do these proofs to some extent only. Randomly we could have positive results for the proofs after an errant calculation. But it is a rare incident. It is a very low probability to happen such a thing. Then what's the reason for these crazy events? Now, let's inquire what mechanism executes in these procedures. As we previously discussed, any integral number in the world is made of a multiple of 9 and the sum of its digits. So that let me consider the two numbers a and b as this. A equals 9n plus x. B equals 9m plus y. Herein, x, m, and y are integers. Then observe what I'm gonna do. I'll add these two numbers. A plus b equals 9n plus x plus 9m plus y equals 9 times m plus n plus x plus y. X and y are the numerical indices of a and b, respectively. Since a plus b has a multiple of 9 which is m plus n times 9, x plus y is its numerical index. So according to this equation, when two numbers get added, the total of their numerical indices must be the same with it of the total of the two numbers. As well, a times b equals 9n plus x times 9m plus y equals 9 by 9, 81mn plus 9mx plus 9ny plus xy equals 9 times 9mn plus m x plus n y plus x. Y. Therefore, in that very pattern, when two numbers get multiplied, the multiplication of their numerical indices must be the same with it of the product. Then you would question, can't we do this very task using the remainders we get when a number is divided by 3? Why not? We can. But it's fruitless because that's more complicated than this. We're able to get the same work done more easily, by casting out 9's. Then let's consider another two examples proving the aforementioned facts. I think they will make your knowledge perfect about this. 5,492 plus 1372 equals 6,864. Then find the numerical indices which are the remainders when each number is divided by 9. Those are 2, 4, and 6. 2 plus 4 equals 6. So our rule is correct. 257,813 times 2,481 equals 639,634,053. The numerical indices are 8, 6 and 3. 8 times 6 equals 48. The numerical index of 48 is 4 plus 8 equals 12 and 1 plus 2 equals 3. This is the numerical index of the product. So this proves our second rule. Now, let's consider the proving by 11s. This is directly not the numerical index, but something related with it. Observe what I'll do on this number. You have to add together alternate digits of the number, beginning from the units digit. And when you've reached the left corner of the number, return, subtracting the alternate digits which still remain, from the sum you've obtained. What is your outcome? If your result is 0 or a multiple of 11, the number is exactly divisible by 11 without any remainder. Otherwise, if your result is not 0 and less than 11, it is the remainder when the number is divided by 11. If you've obtained a result which is greater than 11, subtract the closest multiple of 11 from it, which is less than it. The final answer you get will be the remainder. If you've got a negative number, add 11s until it becomes a positive number which is less than 11. Then it'll be the remainder. Since 8 is a positive number and it is less than 11, 8 is the remainder when this number is divided by 11. Let's look at some other examples. Example 1. 191,919. This process requires an odd-digit number. Why? To find alternate digits. Unless is it, you have to put a 0 in front of the number, as it makes no effect on its value. 9 plus 9 plus 9 plus 0 equals 27. 27 minus 1 minus 1 minus 1 equals 24. As it's greater than 22, reject 22. The remainder is 2. Example 2. 30,698,275. We have to put a 0 to the front because it is an even number of digits. 5 and 2, 7, and 9, 16, and 0 equals 16. Then subtract a3, 6, 8 and a7 from 16, and it is negative 8. As it is a negative number, add an 11. The remainder is 3. Then let's inquire what mechanism executes here. Any real integer like this can be expanded as an addition of the orders of 10 like this, cause this is a number of the base 10. When we considered the numerical index, we managed to convert any integer into an addition of a multiple of 9 and the sum of its digits. Hence here we have to extract a multiple of 11 out of the number. Let's see how we could do so. 99, 9,999, 999,999 and so on numbers are multiples of 11. So we can replace 110,000 as this. See again very well. 99, 9,999, 999,999 and so on. These numbers consist of an even number of 9s. Numbers with an odd number of 9s are not multiples of 11. But 11, 1001, 100,001, and so on are multiples of 11. There are an even number of zeros between the couple of 1s. Hence 10 and 1000 can be replaced as this. Finally we can find the number as an addition of a multiple of 11 and the result obtained after the process we did. After extracting 11s out of that result, the final result we can have must be the remainder when the particular number is divided by 11. Now we have to find the reason for this. Just like previously mentioned, we can take the integers a and b in this type also. A equals 11n plus x. B equals 11n plus y. Look how they get added and multiplied. A plus b equals 11n plus x plus 11n plus y equals 11 times m plus n plus x plus y. A times b equals 11n plus x times 11n plus y equals 11 by 11, 121mn plus 11mx plus 11ny plus xy equals 11 times 11mn plus mx plus ny plus xy. So we can use the aforementioned rules related with not only 9, but with 11 also, in order to prove whether the mathematical executions we do are correct, to some extent. But again I say that, for that requirement, the method of casting out 9s is totally easier. Thank you for watching this video. If you gained something from this video, don't miss to like it and share it. Subscribe my YouTube channel for more video like this. Click the bell icon for getting a notification about my channel. See you again.